Folks can hear me? Confirmation on Teams? Yes. Cool.
They can hear.
Yeah. All right. Sorry for the delay with the screen sharing and all of that. Yeah, so hi, I'm Nick. I am one of the core maintainers of Wasmtime, and here to give you a little update about Wasmtime. So I want to talk about, why would you want to use Wasmtime in the first place? And I think it's really the same reasons that you might want to use WASM. And those are security, performance, and portability being like the real big ones. If you're running untrusted code, hopefully you already care about security. For example, if you're running third-party WASM plugins in your application, or you're maintaining a WASM function as a service platform. But even if you're actually only running trusted code, I think you still actually really care about security. And this is because correctness and security are really deeply intertwined. And when we design for security, we can limit the user impact of bugs. We can do this temporally, for example, where each HTTP request that's handled by your WASM application is kind of isolated from future requests and handled independently. And so a bug in the current request doesn't affect future requests and every single request that happens for the rest of the process lifetime. And we can also do it spatially, where if we have multiple running WASM instances, a bug will only affect this one particular WASM instance, and it's not going to affect other WASM instances or the post process or whatever. And this helps. This helps applications that are embedding Wasmtime, even if they aren't super security focused, because ultimately, if your application is more secure and you have these sort of properties where bugs can't run rampant, then you're more productive. There's less action at a distance. And so Wasmtime both is designed with this sort of stuff in mind. And so like a recent example is the way that we're implementing WASM GC. We're sandboxing the GC heap in the same way that linear memories are sandboxed. So it's a bug in one WASM GC instance doesn't affect any other WASM GC instances. And then also Wasmtime helps enable applications to use this sort of sandboxing themselves when they're running WASM. And so, I think we've all probably seen at this point that Google, Microsoft, and Mozilla all independently found that about 70% of vulnerabilities in their browsers were, root caused by memory safety issues, such as use after free, out of bounds accesses, things like that. And it's even starting to look like the government might legislate that certain applications or contracts that they give out, must be written in memory safe languages. So you don't want to be left behind. You should use Wasmtime because Wasmtime's written in Rust, which is memory safe by default. But of course, you can opt out of that memory safety with unsafe code. And so a lot of the rest of the stuff we talk about with security is going to be about addressing that. But also, much of Wasmtime is free of unsafe code. And we do a ton of fuzzing. We do it ubiquitously. When we write new features, we develop new fuzzers alongside those new features to kind of really hammer on them and exercise them. And this is really one of the biggest factors for Wasmtime's code quality and correctness. We do differential fuzzing between Wasmtime with optimizations versus without optimizations and make sure that we get the same results either way. We run the same program in other engines like V8 and then make sure that we get the same results. And all of that kind of stuff. We also do formal verification, where we're actually formally proving that certain correctness and security properties are upheld. For example, we've actually verified our lowering from our sort of architecture independent mid-end IR into machine instructions. And this proves that each of our kind of rules actually implement the same program snippet. And so Wasmtime also implements WASI and the component model standard, which give us capabilities-based security. So this means that a component, can only access the special powers that you explicitly give it. And it means that a markdown renderer that you don't give access to the network can't use the network. And so therefore it cannot, try and exfiltrate stolen secrets via the network because it just doesn't have access to the network. We also do a bunch of stuff for supply chain security for our dependencies. So you know that we're not going to be hit with like a left pad or something like that. And then, of course, the best laid plans need to have backup plans for when things go wrong. So we have, guidelines for how to report security vulnerabilities responsibly. We have a run book for how to handle, new vulnerabilities. And then we publish, advisories and do public disclosure responsibly as well, and backport security patches and everything. So the second reason you might consider WASM, and therefore also Wasmtime, is performance. And when people think about performance, usually they're thinking about like WASM runtime and compile time. And Wasmtime is competitive on these metrics. We're roughly on par with other optimizing JIT compilers like Wuyts, Turbofan. In general, WASM runtime is usually somewhere around like 1.5x, the equivalent of like compiling that same program to native. And this kind of holds true across many different engines. And in some way you can kind of consider this the cost of gaining everything else that WASM gives you. But of course, we're also trying to identify ways to reduce that cost all the time. And we are trying to do this kind of at the WASM language level, so that all WASM implementations benefit by making new core WASM proposals for new core WASM features and instructions. For example, Alex and Jamie Sharp have been spearheading a 128-bit arithmetic proposal to speed up some big num libraries and crypto stuff. So that's great. So yeah, CraneLift is our optimizing compiler. Compared to a AOT compiler that does tons of optimizations like LLVM, it's an order of magnitude faster. And then compared to something like V8, it's in the same ballpark. Winch is the single pass baseline compiler, so this is going to give you faster compile times than CraneLift, but it's going to have slower runtime, so it's a trade-off. But although most people usually talk about compile time and runtime, and they talk about performance, I think it's actually not one of the most important aspects of performance. I think what's really important is how fast can you spawn new WASM instances, because it unlocks so much more that's really unique and exciting about WASM. So Wasmtime can spawn a new WASM instance in 5 microseconds. It's basically bottlenecked on the operating system's virtual memory implementation. So you can compare this to spawning a new virtual machine, container, or process, all of which are magnitudes of order slower. And this really enables that disposable instance paradigm, also known as temporal sandboxing. This is where, for example, in a function as a service platform, each HTTP request gets its own WASM instance. And then for the next HTTP request, we use a new WASM instance and everything gets reset. And then this also means that you don't need to have server processes kind of sitting idle and waiting for work to come in and kind of wasting CPU and memory overhead. All of that is kind of unlocked by having fast instantiation. And ultimately, this gives you greater density. And so, given the same amount of resources, people have measured, our friend at Fermion, for example, that Wasmtime can run, on the order of 50 times more concurrent WASM instances than you could fit containers in Kubernetes on the same machine. So that's huge. And kind of the final big reason you might choose WASM and Wasmtime is because you don't want to target just one particular platform. You want portability. And so the goal is basically to bring Wasmtime and therefore your ability to run WASMs anywhere. So right now, our releases include binaries for 11 different platforms. CraneLift targets 4 different instruction sets. We have no-stud and bare metal support. You can even compile certain configurations of Wasmtime to WASM itself, which is kind of interesting for if you want to sandbox the compiler and have the same kind of controls over interruption and everything that regular WASM, running WASM has. And then we have APIs for embedding Wasmtime in Rust applications, C applications, etc. So, kind of the idea is whatever language you're writing your application in, you should be able to pull Wasmtime in. So now I'll get into a little bit about what we kind of focused on in 2024. And looking back at all of our release notes, I kind of identified 3 big areas of focus. But then, there's always a lot of like random little stuff. So those areas of focus are, WASI P2, WASM GC, and portability. So huge congrats to everyone who worked on getting WASI P2 shipped, both 020 and 021. We added Semver-aware linking to Wasmtime so that you can kind of automatically get the right version of your WASI imports. A ton of people did a lot of work on resources and the host APIs for working with resources. We saw I/O improvements, performance improvements, and bind-gen improvements. I am going to just asterisk this and say that I haven't been the most involved in the WASI effort, and so I'm going to be a little bit more brief about this stuff just because I'm not as knowledgeable. So apologies for that. What I am knowledgeable about is WASM GC because I'm implementing it. And so here, the goal is to run, more languages on WASM and Wasmtime, kind of the, some of the final frontiers of getting stuff onto WASM. We're almost done. As far as, spec correctness and passing, the spec test suite and all of that goes, we're 95% of the way there. It's really just kind of like checking the final boxes at this point. As far as production ready quality of implementation wise, there's still some more work to be done. So I'd say it's about 75% and expect it to be finished by the end of the year. So a ton of stuff has happened. All of the type system changes are finished. So now you can define struct and array types, and subtyping relationships. We have GC heaps that are sandboxed, and so we're not using, regular malloc or whatever, and so bugs in the garbage collector are basically limited to just that GC heap and can't affect the rest of the program or the host. All of the struct instructions are done. The array instructions are done. Asterisk, I haven't actually landed them yet. And we have, embedder APIs so that the host can define these types and allocate and manipulate objects and all of that stuff. What's still to be done are, basically a few instructions just to check off. All the stuff that's required to implement them is basically done. It's just about kind of doing that last little bit of plumbing. Right now, we don't allow funcrefs in the GC heap because we don't trust anything in the GC heap, and funcrefs are implemented as raw pointers, and so we need an indirection there, and that just hasn't been implemented yet. The kind of biggest outstanding item, I think, is the implementation of the copying collector. Right now, we're still using the deferred reference counting collector that we used for extern-ref, but we want to be able to have a copying collector and also a null collector that just lets you allocate but doesn't actually collect anything. And pooling allocator integration and lots of optimizations are left to do. As far as portability goes, at the end of 2023, we landed the initial no-stud support and kind of bare metal support where embedders can implement a certain header, and then Wasmtime will just use the interface from that header and not rely on any kind of OS APIs or anything like that. We've added a mode where Wasmtime doesn't depend on signals or virtual memory at all. So that's just less dependence on OS APIs for those cases where you're in interesting situations. And we also added compile time features for just about everything in Wasmtime. And so this lets you disable features you're not going to use and get a smaller binary that's more appropriate to, say, an embedded environment if that's what you need. So for example, you can disable WASMGC at compile time, and then we aren't going to build the garbage collector, and we're not going to include the binary code for the thing we didn't build in that final binary for Wasmtime. Wasmtime.wasm, I talked about that earlier. And we added a few new release binaries as well for new platforms. We also championed the custom page sizes proposal in the WASM CG. So the goal here is to provide a standards compliant way to support like really small embedded environments that use a WASM memory by default is 64 kilobytes, but that might be more memory than is really available for the embedded platform in the first place. And so the goal here was a standards compliant way to support smaller than 64 kilobyte WASM memories rather than doing kind of like ad hoc non-standard solutions. So this is currently phase 2 in the standards process. And actually, if you look at technical requirements, we already satisfy everything in phase 3 and already did at the time that phase 2 vote happened. So it's just kind of waiting to be incremented to the next phase. And this is fully supported in Wasmtime. And really all that's needed next is some WASM LD support and to go to the next phase. And kind of the final spearhead of portability is Poly, which is a portable optimizing interpreter. And so the goal here is to be able to bring Wasmtime to any kind of target that Rust-C can compile to, or LLVM can compile to, including ISAs that CraneLift and Winch do not have a backend for, because the current state is that if CraneLift or Winch can't compile code for that instruction set, then you can't run WASM there. And so the idea is if we have a portable interpreter, then you don't need to write a compiler backend for any new instruction set before you can start running WASM there. And then the secondary goal is execution speed of WASM. And the reason for this is because if you're in a situation where you don't have access to our optimizing compiler, then you need everything else you can to really try and recover speed as much as possible. And so then that means there's also certain things that are not goals. Being a very simple reference interpreter is not a goal. WASM already has a reference interpreter, and it does that job fantastically. It's not designed to be an in-place interpreter, kind of giving you the very, very fastest startup from WASM to execution. Because in order to be a fast interpreter, we want to kind of do some bytecode rewriting and translation and stuff. And so that kind of precludes being an in-place interpreter. And we're also not trying to do any sort of dynamic tiering from the interpreter and then going up to JIT code after the JIT code's compiled or ready. It's just not a goal at this time. So the design of Poly was basically followed from the insight that the first thing that interpreters do to get fast is kind of optimize their interpolation loop. But after that, the next things they start to do is translate to an internal bytecode format rather than the original bytecode format, like translate WASM to some kind of interpreter-specific bytecode format. And they do things like turn multiple WASM operations into a single macro op or a super instruction. And then generally run optimizations on that bytecode as an optimizing compiler otherwise would. And it turns out, well, we already have an optimizing compiler that we maintain. It's called CraneLift, and it already implements a lot of great optimizations like global value numbering, loop invariant code motion, various p-pole rewrites, etc. And in fact, we developed this language called ISLE for doing kind of pattern matching rewrites. And so it's already got really great support for matching multiple kind of input instructions and turning them into like a more complicated output instruction, which is basically what that kind of macro op or super instruction fusing is. And so all that was really missing was kind of a bytecode format, an interpreter that could interpret that bytecode format, and then a crane lift backend that could take, WASM in and then spit out this custom bytecode format after running optimizations. And so that is sort of what Pulley is those three things. And so what has landed is the bytecode format definition, along with an encoder, decoder, disassembler, all of which are kind of mechanically generated from the same, I guess, like spec description of the bytecode. And we also have a crane lift backend now that will emit this stuff. What is not implemented yet is the actual integration of Wasmtime's runtime and pulling in that interpreter. I have an old prototype branch that needs to be rebased and kind of reworked, but it's not landed yet. And of course, it's not complete. It mostly just does like adds and a few loads and stuff like that. And so there's a lot more WASM instructions than that. And so we need to kind of just round out completeness. And of course, once we have completeness, we can start talking about perf optimization. All right, so now we're going to start getting into just a bunch of little miscellaneous stuff that we worked on in 2024. Did a bit of work on kind of developer tooling. Yes, this is where I am.
Yeah, we weren't sure if we were gapped.
Yep. No, great. Looks good.
Do you mind just stop sharing and reshare?
Yeah. Give me a second.
Yeah,
Those
it
are
was
different
now.
titles.
It was now, yeah.
Well, all right. Is that sharing?
It's still stuck on the progress in 20, the portability one. We see Nick. That's pretty strange.
Just stop doing. Are you seeing debugging and profiling now?
Hang on a second, Bailey's name. This is right here. This is right here.
Yeah, sure.
Phil's legendary.
Till.
Right here.
Shen Isom.
Right here.
Shen Isom.
I disconnected. I think it's easier to not. Thank you.
We're gonna troubleshoot for a minute.
case, especially for the language service. It's simply
If you just get back to where we were.
all of these phones. But
All right. Yeah. So we also did a bit of developer tooling work in 2024.
Hey,
So-
Nick,
Yep.
the screens are off now.
It looks great on
All right.
Teams.
I will
then we
just do.
you can
two
I
computers at
only have
once.
this or that.
Teams Pro, you can only be at on one team at a time, I guess.
That's their assumption.
Okay. And
It's very
there.
So your language service.
Where?
There it goes. Nice.
Cool.
The clapper.
Confirm we still have Teams now. Yes.
Great.
Yeah, yeah.
All right. Thanks for the patience, everybody. So yeah, so we have some.
They are not types.
So we added initial support for debugging components to our existing debugging support. This is the one that kind of lets you attach GDB or LLDB to a whole Wasmtime process and then debug both the Wasm guests and Wasmtime itself. And we also added support for split dwarf, where the dwarf is kind of in separate files on the side, as well as a variety of guest profiler improvements like symbol demangling and stuff like that. And we also had a bunch of crane lift and Wasm code gen improvements and performance improvements there. So tail call support was added to our S390X backend, which means that it's now supported on all targets. We also improved the performance of tail calls, and therefore we enabled tail calls by default. We optimized the implementation of call indirect for Wasm to have less branches and less indirection. We added compressed instructions for RISC-V, optimized NAND canonicalization if that's something you're using to get deterministic NAND bit patterns. And then, of course, lots of little optimizations here and there, various instruction lowerings and things like that. Winch, our baseline compiler, also saw some improvements. So it completed support for all of Wasm 1.0 on the x86-64 backend. It added component model support and also memory 64 support. We have a contributor right now working on an AR64 backend for Winch as well. And then we also implemented the extended const proposal and enabled it by default as well. And I didn't know how to group that. I'm sure there was other stuff we also did. It was a lot of release notes to go through. So apologies if I missed anyone's favorite feature or something like that. So now let's look ahead to 2025. So first, let's take a look at kind of our community size and contributions that we're getting. So looking at the last year, looking at this past year, but that same window last year, we had 138 contributors and 1838 commits. And this year we actually got one more contributor, but we're down about 390 commits. So commits are not everything, but they're kind of like maybe the closest signal that we have to the things that we do actually care about, which is how much work is happening here. And so I kind of dug in, and it turns out Wasmtime maintenance is unevenly distributed. This is both at an individual level and an organizational level. So Alex alone is an unstoppable machine who contributes a whole third of all commits. And then at an organizational level, between Fermion and Fastly, that's 2/3 of commits, and no other Bytecode Alliance organization accumulates more than 5% of commits. And kind of the asterisk next to Fastly is because 3 of our top 7 committers have actually left Fastly, are no longer employed by Fastly. and they haven't been hired by any other Bytecode Alliance organization. And the result is that they're no longer contributing to Wasmtime. So we have this, already unevenly distribution, or very uneven distribution, and then 3 of our top 7 are kind of going away. So that means that the real distribution is even more uneven than this. We just haven't fully seen the result yet. So that's why for 2025, I think our biggest goals in the Wasmtime project really need to be to promote people from being occasional committers and turn them into frequent committers. But that's not something that we can just do on our own. This is something that kind of requires additional organizational investment in Wasmtime. So if you are building on top of Wasmtime, but you're not contributing to foundations, I ask why that is and what we can do to make that easier and help you out. In general, the people who are contributing to Wasmtime and maintaining it are doing so on behalf of their organization use cases and application, and specifically what their organization needs. And so the result is that Wasmtime is very good for how it's being used by those organizations. And so the best way to make Wasmtime really good for your specific needs is to get involved and start contributing. And so if you're interested in that, come talk to me. There's also a variety of things we could do in 2024, if we had cycles and someone picked it up. 2025. So this includes a bunch of WASM features like exceptions. These are phase 4, which means basically done. And we have an open RFC kind of discussing a strategy for how we want to implement this stuff. And we just haven't gotten around to it yet because we don't have the cycles. So toolchains are starting to assume support for exceptions because of how mature of a proposal it is. But because we don't support exceptions, if toolchains just start using exceptions by default, that means that those WASMs aren't going to run on Wasmtime anymore. Just in general, beyond being able to continue to run WASMs in the future, exceptions are useful for Rust, for Panics, for C++ exceptions, Go, .NET, Ruby. Basically, everyone can take advantage of exceptions once they exist. Another is stack switching, which is really exciting. It's kind of been around for a really long time, but hasn't been making progress in the community group. But recently, kind of the impasse has been unblocked. So it moved to phase 2, but I expect it to go to phase 3 very quickly. And I think it's really exciting because there's a lot of potential for big speedups here. So I want to highlight that the experiments we did were very rough, very, very early experiments, just to kind of see, TinyGo right now is using Asyncify to kind of, work around the lack of stack switching. And so we kind of did, well, what if we don't Asyncify and see how much better performance can get for TinyGo? And we saw a 2x speed up by not using Asyncify. And so that's sort of for this one very rough benchmark or experiment, that's sort of the speed of light of how much faster we could get with stack switching. And I expect we would be able to get very close to that kind of theoretical 2x speed up. So that's really exciting. And we kind of want this for full async in WASI in the component model. And it's just generally useful for .NET and Ruby and Python. Anyone else who's doing async or kind of cooperative green threading is going to want this. One thing to note is that it does spec-wise kind of depend on exceptions. So we would want to implement exceptions kind of before getting too far down the stack switching route. Another one is shared everything threads. This is a phase 1 proposal, and it enables kind of proper multi-threading in WASI in the component model, and allows basically every kind of entity that exists in WASM to optionally be shared across threads. I'm not going to talk too much about this because Andrew Brown is going to give a talk. I can't remember if it's later today or tomorrow, about shared everything threads. But yeah, he's started implementation in like WASM tools and is poking at Wasmtime and stuff, but there's still lots to be done to get this in a kind of production ready, well, first implement it at all and then kind of production ready. So if you're interested in multi-threading in WASM, this is a good place to jump in. Another thing we could do is really invest in debugging. We actually merged an RFC describing kind of our North Star for what we want debugging to look like in a year or two, whatever. Things like the debug adapter protocol and VS Code integration, among other editors, support for core dumps and setting breakpoints and watch points and all that stuff. And even how we want to build time travel debugging and deterministic record and replay. As well as kind of debugger components that allow source level debugging of programs that aren't themselves compiled to WASM, but are actually programs being interpreted in a runtime that the runtime is compiled to WASM. So this would be things like debugging a JavaScript program that's being interpreted in Starling Monkey. And so there's some really cool, magical developer tooling we could build here, kind of leveraging WASM's strengths of like enumerating exactly what is the state in a WASM instance and everything to kind of do that record and replay and stuff. We've had these ideas for a while. We actually originally intended to start this effort, around now, but it was deferred due to lack of cycles and availability among core Wasmtime contributors. So if developer tooling is something that you're really interested in and want to invest in, this is another great place to jump in. And of course, performance is something that can always be improved. This is kind of the Sisyphusian task of working on a language runtime. We can improve code gen and speed up, WASM runtime execution. Lots of things we can do: register allocator improvements, work on inlining across components so that when you split things into little components and then glue them together.
More context for remote attendees will love being here, but it's better now.
All right. Yeah, so if you split your application up into many little components and then kind of glue them together again, it'd be nice if we could inline those functions across component boundaries. Newer WASM features are always ripe for optimization because we haven't spent as much time looking at their code yet, right? So there's we could do escape analysis for WASM GC, type-based alias analysis, bounds check elimination, lots of stuff we could be doing. And as well as ways to kind of lower the overhead of running interruptible WASM. So if you want to be able to run WASM, but then kill it if it gets in a infinite loop, that implies kind of some extra instrumentation and stuff like that, collaboration with the runtime. And that adds overhead over, if you didn't have that WASM be interruptible. And so we have ideas of ways that we can actually make that overhead smaller. Yeah, so if you care a lot about performance, this is another great place to start contributing. And of course, there's all of the work on Pulley that I talked about earlier that was still to be done. If we kind of get Pulley in a good place, then that means we can bring Wasmtime to new targets that it can't go to right now. And we could start adding binaries to our releases for ARM-v7 or RISC-v32 or Extensa or something like that. We could work on code size improvements for Wasmtime. It's something that no one has really worked on because no one's had the use case. No one who's using Wasmtime in production has had the use case of wanting a small Wasmtime binary. But there's lots of low-hanging fruit if there were interested parties. And similarly, Wasmtime works for Nosted right now and bare metal, but it it's in that state where it's working, but no one's actually using it in anger yet. And so it kind of reflects that, right? Like there's just polish that could be done to make it easier. And this last bullet point, I didn't really know where to put it, so I threw it here. But like, we could start prototyping support for caller-provided buffers in the component model and kind of looking at ways that we can remove the requirement for allocators and stuff like that. Yeah, also, I think we could, take a hard look at our documentation and kind of improve the story there. I think it would be really cool to have a cookbook with recipes for kind of like common use cases for WASM, or what people want to do with Wasmtime. Say, oh, I want to build a plugin system for my application. Here's how you do it. Or I want to send WASM binaries to iOS and Android and the web, and kind of have them work everywhere. Here's how you do that with Wasmtime. I want to build a function as a service platform. Here's kind of the architecture that you should use in order to make the most of Wasmtime. Can always add more examples and more polish the documentation. I think it would be useful to maybe do a pass over like what some other WASM runtimes document, and then kind of cross-reference that with the documentation we have, and make sure that we're not missing any, have any large gaps. So yeah, I just want to say thanks to everyone who contributed to Wasmtime in 2024. And thanks to Chris and Alex for providing some feedback on early drafts of these slides. And yeah, that's it. Thanks.
To answer some questions.
Yeah, I just wanted to check timing.
We have 4 minutes.
4 minutes? Okay, I have 4 minutes of time if people have questions. Yeah.
So I have 2 questions. So one is about the ARM64 support in the Wasmtime. I'm just curious about the current status. I saw you have the plan to add the ARM support in 2025 next year. Another question, I know the Bytecode Alliance has 2 WebAssembly engine. One is Wasmtime and one is a WAMR that called WebAssembly Michael. Well, I don't remember the full name. So I'm just curious, is will you maintain that, continue maintaining the 2 engines, or will like the WebAssembly, the Wasmtime will be the future like the engine?
Yeah. So the question, in case it didn't get picked up by the ceiling mics for people that are virtual, was sort of what's the status of the ARM64 support in Wasmtime, and then I guess curiosity about the status of WAMR and
Features between the WAMR and the Wasmtime.
Yeah. So I can't speak too much for the WAMR team. They do have a talk scheduled for this evening, so they can answer more about that. And I'm just also less familiar with their status. Our AR64 is support in Wasmtime is very mature. There's lots of people who are regularly developing Wasmtime that are on M1s, and so they're working with it every day. Let's see. So the crane lift support is very good and very complete. Crane lift being the optimizing compiler. What I have on the slide that I'm showing now is that the winch support is still in progress, and so winch is the baseline compiler. So that's one thing to note. I think the only thing that's holding AR64 back from being, we have what we call tiers of support in Wasmtime. The only thing that's holding it back from being tier 1, which is the highest priority, is continuous fuzzing. We have a requirement that all tier 1 features or whatever are continuously fuzzed, and we use OSS fuzz for that. But OSS fuzz doesn't support AR64 right now, so it would require someone to invest time setting up a box or something, right? But other than that, it's I would say it's pretty much tier 1 in all but name. Yeah. Any other last questions?
Yep. Did you say that LLDB debugging was working in components now?
Yeah, for certain definitions of working. Yeah, so what Wasmtime does now is it receives the WASM, which has dwarf, but it's dwarf that's talking about WASM locations, right? It's going to be talking about WASM locals as its registers and stuff like that, right? And then when we compile the WASM to native code, we also produce debug info that tells us the mapping from the WASM level to the native code level, and then we use that debug info to rewrite the dwarf subscript WASM into dwarf subscript native, and then there's like GNU APIs or platform-specific APIs to register to dynamically register dwarf for JIT code. And so we do that for this. And then when you attach GDB or LLDB to the Wasmtime process, you can end up stepping through the guest. You also end up stepping through the host, which is not what most people want, 99% of the times. But it works okay. Yeah, I think there's really cool kind of like first class debugging support we could build, but that's going to be sort of like us building the debugging and then serving over the debug adapter protocol rather than kind of shoehorning into a native debugger scenario. Got it. Yeah, last question.
You have a slide talked about formal verification in security of Wasmtime. I'm just wondering what specific methods are being considered for the formal verification of the WASI implementation in Wasmtime, and how would they address like potential issues with like file system access or network isolation?
The WASI implementation?
Yeah.
I know that there have been people who have been talking about verifying that the component model and like fused adapters properly sandbox between different components and don't leak data that's not explicitly handed across that boundary. I don't know of anyone that's working specifically on like the syscalls, but maybe Phil does.
I know that UCSD has done some work on actually, I mean, before you formalize or build a proof system for an implementation, you actually need to have semantics for the syscalls, and that for a lot of the what WASI is about is extremely difficult to come by because the systems you abstract over across multiple different platforms often end up just fundamentally not having a well-defined semantics to begin with. So there are kind of limits to what we can do there. There has been some work again at UCSD for doing this for the WASI P1 subset for the more traditional POSIX things. I don't think they ever published a paper.
Chris Fallon linked a PDF from UCSD, and he called out Evan Johnson as being doing that work.
Thank you.
So everybody, round of applause for Nick. Thank you.